everything. So Paul, why don't you get started?
And it actually,
okay, so welcome to lecture number 5. So my original plan for lecture number 5 was that I was going to sort of talk about the application of hydrodynamic models to actual IO collisions. And I will do a little bit of that, although most likely what I'll sort of end up doing is I'll sort of give a focus on one of these particular topics. I will focus on the early time dynamics before hydrodynamics, and I will use in particular strong coupling techniques, AdS CFT correspondence, to sort of get at that. So from discussion with some of you guys, I got the impression that many of you sort of know very well how sort of the relation between hydrodynamics and kinetic theory sort of works out. So I'm going to sort of pretty much neglect that part, and I'm going to focus on the strongly coupled part, in particular how hydrodynamics and strong coupling approaches sort of work out. To sort of maybe sort of set the stage for this, I would like to sort of maybe sort of start by drawing a diagram that sort of, excuse me, that is supposed to picture some of these things that I just said graphically. And the idea behind that is that we sort of talked quite a bit on hydrodynamics as an effective field theory, and that its region of applicability had really sort of nothing to do per se with equilibrium. So the way that I like to sort of phrase it is that I would like to talk about regimes of applicability of various approaches. And the way that I'll sort of structure this is that I will sort of have a 2-axis diagram where on the lower part I will write down the interaction strength. And on the vertical axis, I will write down the gradient strength. So the idea behind this diagram is that we can sort of think of, let's say, quantum field theories that either are very weakly coupled, so they have very small interaction strength, or they're very strongly coupled, so they have infinite interaction strength. And we can think of these quantum field theories in a second sort of direction, in which we take the quantum field theory but we expose it to some sort of gradient, where no gradient, zero interaction strength would mean we take the quantum field theory in equilibrium, and we can sort of raise the gradient strength until we get to a regime where the gradient strength is essentially infinite. This would be extremely far away from equilibrium. And in this diagram, we can sort of put certain sort of regimes. So, for instance, if the interaction strength is very, very small, then we have a sliver here, which you usually sort of can access by perturbation theory. Because that approach is not limited to having a particular gradient strength. We can talk about far from equilibrium problems in perturbation theory, and there's no issue as long as the coupling is small. Okay, and if you want, so in some sense, sort of the sort of application of, for instance, classical chromodynamics to heavy ion collisions, this color glass condensate approach is one application of this, where we say, okay, we take the coupling to be small, so we have effectively a classical equation of motion that we can solve even if the system evolution is far away from equilibrium. Okay. On the other hand, we can sort of take approaches where essentially the gradient strength, for instance, would be very, very small.
Just to check, so that region, you're saying no matter where you go, it's still analytic in the strength. There's no phenomena that
Right. So okay. The question is whether this really sort of is a well-defined statement for all sort of interaction strength. And I would say generally yes. However, there can be phenomena where you have non-analyticities. That's possible. Although if I go all the way to 0, then I would sort of claim that most likely we don't have any issues. If the theory is not defined, if the free theory is not defined, then we really don't know what the theory is. So usually the way we sort of interpret quantum field theories is that we write down a Lagrangian that is well defined in free theory, and we do perturbations around it. So I would claim that there is this sliver where we sort of have analytic control of what's going on, no matter what the interaction strength is.
Yeah, I was just thinking something that had like an essential singularity.
Right. So we are not aware of at least many instances of this. That is no proof that that can't happen. Okay. On the other sort of axis, we can sort of think about systems that have very small gradient strength, but are basically arbitrarily strongly coupled. And one approach that sort of works very well there, in sort of the corresponding slip over here, would be, for instance, like this field theory. So this is a theory that is, sort of strictly speaking, well defined as long as you're close to equilibrium, because then you can sort of essentially Monte Carlo your action, and the complete non-perturbative nature of the problem really doesn't play that much of a role. You can essentially get reliable numerical results no matter what the coupling is. Okay. So I started drawing out these things. You can sort of put many things there, but what I would like to point out is that something that has not been really sort of emphasized in these lectures, which is that you can also sort of put the applicability of fluid dynamics in this regime. And loosely speaking, you can already sort of see that from this old textbook criterion that I had, where you want to sort of have the mean free path over the system size to be smallish. And if you sort of recall that the mean free path in a relativistic system is given by the ratio of epsilon eta over epsilon plus p, which you can write as eta s times 1 over t. You sort of just say that this has to be smaller than 1. If you plug this in here, you find that fluid dynamics, you expect fluid dynamics to be a good approximation as long as this is small. And in order to sort of plug this into this diagram here, essentially all I have to do is that I have to sort of know how does this transport parameter vary with the interaction strength. Well, we kind of know how that goes. So typically have that this essentially goes like 1 over the coupling, which I also call lambda, this is bad, 1 over coupling squared, loosely speaking. So what that means is that if the coupling is strong, then the viscosity is small, and that means you get a larger regime of gradient strength. This is the sort of effective inverse system size for your applicability of fluid dynamics. And conversely, if the coupling is small, this ratio is large, this shrinks your applicability. So the upshot of the story is that you have a sliver that sort of looks sort of like this. Fluid dynamics. It says that if the interaction strength is 0, you have a free theory, there is no sizable application for fluid dynamics in a free theory. Okay. So this is conversely to sort of many of the other approaches that we have. Fluid dynamics works best, so the regime of applicability in terms of gradient strength is largest if the coupling is strong. That's because then this transport coefficient is small and we have a large range of gradient strength values that we can access. So I wanted you to sort of be aware of that, because that's oftentimes conception is sort of an issue when we talk about sort of when fluid dynamics applies. Fluid dynamics sort of is, if you want, so a complete sort of opposite of perturbation theory. It works best if the coupling is strongest.
So area conditions begin, I presume, with large gradients. So up, and if this in the perturbative picture, there would really be no other color of the
So the question is about the question is about where do heavy ion collisions fall in this. So presumably at very short times after the collision or at the collision time, we just have high energies That means that you're approximating, or you're taking the QCD coupling strength at that high energy scale, so presumably the coupling is not that large. It will not be sort of zero, but it will be some smallish value, so presumably you start outside the regime of fluid dynamics. But then as the system sort of expands and cools down, your relative energy scale that the coupling is measured will drop. So the coupling, because of asymptotic freon, will go up. And at some point, you sort of will enter, the gradient strength also goes down. At some point, you basically will enter the regime of fluid dynamics. So what I want to sort of talk about today is precisely this sort of early time region. If I have time, I will do both the weak coupling and strong coupling approach. But let's see how far we get. So I will start with the strong coupling approach first.
Do you have a big blank space there? Is there anything in there?
Yes, there are things in there. In particular, kinetic theory sort of has the shape that so kinetic theory needs well-defined quasar particles. So it's basically its biggest regime of applicability is if the interaction strength is small. So the way that I would sort of characterize something like this, so this would be kinetic theory. So what you can also then see from this plot, which doesn't have any extra numbers on the axis, is that nevertheless there is a regime where many of these things are actually overlapping, in particular kinetic theory, fluid dynamics, lattice field theory. However, there's also a regime, for instance, that strong interaction strength, where you have fluid dynamics, but no kinetic description. Okay? And that's an important point because many standard approaches of fluid dynamics start out here and discuss fluid dynamics exclusively as a limit of kinetic theory. But I think that's just needlessly restricting the applicability of fluid dynamics because it is an effective field theory in its own right. It has a different regime of applicability. In particular, you can use it for problems where you don't have a particle-like description. And what I want to do next is precisely one aspect of this. I want to sort of start with a system that doesn't have a kinetic theory description, at least as far as we know, but it has a fluid dynamics, properties.
What do you say to the philosophy that kinetic theory is perfectly good to derive the structure of the hydrodynamic theory as long as you calculate properties from the actual theory?
Right. So I think this approach may work, but it's dangerous in the sense that there are examples of there is one particular example where you sort of take kinetic theory, you want to sort of calculate the structure of the equations, and you miss terms because the coefficients in kinetic theory happen to be zero, but they don't have to be.
That's usually when you solve kinetic theory in some approximation.
No, that's if you take kinetic theory in curved spacetime, for instance, you don't recover this curvature squared terms.
Oh.
Yeah. So you miss those. And you miss them because in kinetic theory, the value of the coefficients is zero, so you don't see the terms. But they are there in the full description.
Why is that?
I think the reason is that kinetic theory itself is a gradient expansion of the underlying quantum field theory, and it's only first order sort of gradient expansion. So there are some terms that you miss, which are second order. That's what I think happens, but I don't have the proof. I think no kinetic theory that is beyond first order gradient approximation of the Wigner function has been really studied. Are there other questions?
Just a comment.
Yeah.
I think this kinetic theory, when you take it to third-order dynamics, I think as you just said, it misses the terms which are quadratic in vorticity.
Right. Thank you. Yes. So this is just reiterating this point. So kinetic theory also sort of misses terms that have nothing to do with curvature squared terms, but are just vorticity squared, which we know have to be there in general, but kinetic theory misses them because in kinetic theory, the coefficients multiplying those terms just happens to be zero. Okay. So, good. So I have to sort of essentially take a step back and sort of now, so far I've talked about essentially fluid dynamics as an effective field theory. Now I take a step back and I sort of want to sort of study a microscopic theory. I want to sort of study a particular field theory n equals 4 super EMLs for the limit where the number of colors goes to infinity, and the tooth coupling g squared n, which we define to be lambda, also goes to infinity. This is a microscopic quantum field theory, and as such, it sort of has, if you want, the full answer if I'm able to sort of solve the full problem. And I'll show you some aspects of how fluid dynamics emerges from this description. The way I will structure it is that I sort of, if you have, the way I will structure is that I sort of give you these sort of salient features of how to get there, but basically to really sort of know exactly what I'm doing, you basically sort of need quite a bit of background in general relativity. So I will sit to say things like, oh, you solve Einstein equations, assuming that you either sort of know already how to do this or can learn it if you're really interested in how to do it, okay? So in that sense, it will be a little bit hand-wavy, but I'll try to focus on the physics rather than the technical. Good, so why don't I get started with this? Okay, so the way we sort of are taught to sort of approach this problem is that we sort of look at a completely different system. We sort of use gauge gravity duality to sort of map this system to basically essentially classical Einstein gravity in 5-dimensional space-time with negative cosmological constant. So basically the short sort of answer is that we sort of say we are in a space-time that is asymptotically AdS 5. And the superspace is the space-time that has negative cosmological constant, and we have 5 dimensions. How does this work out in practice? Okay, so the way we sort of like to do this is that you write down, so the simplest case, if you discuss empty AdS 5 space, this would correspond to no fluid at all. Okay, this is correspond to empty, the vacuum in any of those super angles. And the way you construct this is that you sort of write down a line element. So we are in 5 dimensions. So this will have a structure that looks like this. This is our usual Minkowski line element, but then we add a 5th dimension, and we allow ourselves to have a prefactor f squared here. So sort of account for the fact that, okay, maybe we don't, it's not just 5-dimensional Minkowski space, it maybe has a different structure. And we can fix this prefactor here by taking this line element and plug it into Einstein equations. R mu minus 1/2 g mu r plus lambda g mu is 8 pi g mu. Okay. So these are Einstein equations. R mu is the Ricci tensor, R is the Ricci scalar, g mu is the metric, so that's this thing here. The line element is always defined as g mu d, or let me start writing GAB for 5-dimensional coordinates. dx, a, exp, where a and b are Latin indices describing 5 dimensions. The usual 4-dimensional ones would be mu and nu, so Greek indices. So that's the metric. Lambda is the cosmological constant, and then on the right-hand side, I have an energy momentum tensor of this 5-dimensional spacetime, and g is Newton's constant, but it would be Newton's constant in 5 dimensions. So I usually sort of write 5 here. Okay.
Sorry, you just said that A and B are 5-dimensional, yes, and your Einstein equations should.
That's correct. Yeah, I should have.
Why don't you do capital like M and N?
It's just notation.
Because A and
A,
B
B,
is
A, B,
string world shape.
A, B. This is my right, and basically we can sort of plug this in here. Then you'll find that this f here is has to have the solution. F of u is L squared over u squared, where L really sort of is proportional to, or it's given by the scale of this cosmological constant. Okay, so L basically is, I should say, so lambda basically can be written as, I think this is right, but -6 over L squared. So this is the relation between L and L. So we have, so basically the point is that if you take this in here, this is an exact solution of Einstein equations for empty 5-dimensional space. So meaning there's no energy momentum tensor there. And as such, it sort of corresponds to sort of the vacuum in any goes. So it's basically our background. It's not very interesting. Now let's make it more interesting. And to make it more interesting, we want to sort of talk about a fluid in equilibrium at temperature T. And to do that, we'll talk about the black ring that you sort of briefly mentioned in one of the earlier lectures. Before I do so, however, let me just point out that if you look at this line element here, you'll notice that so the structure in the numerator here on Real sort of looks like essentially Minkowski space. There's nothing really sort of deep going on, but it has this 1 over u squared in here. So what that means is that this empty spacetime has a singularity at one particular coordinate point. So at u is 0, you notice that it has a 1 over u, so at u is 0, there's a singularity. So it means that the spacetime here actually has a boundary. This we call the conformal boundary. And really what you should think of is that this 5-dimensional spacetime, the structure of it looks like this, that at u is 0, you have a 4-dimensional boundary, and then the rest of the spacetime sort of goes into the bulk, as we call it. So up here is u is 0. This is the 4-dimensional boundary of the theory. It has, if you forget about this, it has just Minkowski metric. So this is where we live. This is M4. And then u basically sort of goes down. So if you're at u larger than 0, you're somewhere in the 5th dimension. You could also call this description a holographic description because holograms in sort of lower dimensions can, as a hologram, can store 3-dimensional information even though it's sort of 2-dimensionally stored. It's the same thing. Instead of talking about really what's going on in this quantum field theory in 4 dimensions, we basically describe it by a classical theory in 5 dimensions. So essentially, you sort of use something that very often happens in quantum field theory is that a classical theory in one higher dimension sort of is dual to a quantum theory in one lower dimension. But the point here is that the AdS 5 spacetime just has this boundary, and this is basically everything we live. This was empty. Now let's talk about the black ring. So the idea now is that we want to sort of talk about solutions that have this character of a black hole, but it is perfectly permissible to sort of look for solutions that don't really have a spherical structure, but they are basically sort of flat sheets. And the way you do it is you basically do the same thing, the same trick as if you were study Schwarzschild solutions in usual Einstein gravity in 4 dimensions. You basically take the line element that you had, s squared over u squared minus dt squared plus, let me just call all the x, y, and z coordinate just dx vector squared, and then we have plus the u squared. And the way you sort of consider Schwarzschild is that you sort of add a vector f of u here, and its inverse in one of the other coordinates. Not the same. One is right. Yeah, that's this maybe bad notation. So this was, yeah. Let me sort of erase this, put it in here, so I have only one f. L squared over u squared. It's a different f. So Yuri wants me to change my notation, and that's fine. It's fine. So and that's basically how you make an ansatz for your line element. And then essentially it's the same idea, okay? So you take this, you plug it into Einstein equations, and you sort of go solve for f. And what you find is that f u is 1 minus u to the 4 over us to the 4, where us is essentially just some constant. At this point, you really don't know very much more than this, except that, well, this is the solution that you get from Einstein equation. Let's look at the structure of that solution again. If you have your line element here, there's a question. Yeah.
Einstein equations for what? I mean, now you're putting a particular source on the right-hand side.
No, it's still empty.
Still empty.
As with Schwarzschild in usual Minkowski.
So what's different between the empty AdS before and this empty AdS?
So now, in particular, my sort of time dilation factor and my other factor have some structure. The global structure of the space-time is different. It's now no longer empty space, empty AdS space. It's now only asymptotically AdS space in the sense that close to our conformal boundary, you can check that this solution sort of is the same as the empty one. So it's still global, it's still asymptotic AdS, but the overall global structure is different because this F here has a 0 at a particular value of u. In particular, this has a singularity. So a singularity at u is us. This singularity is independent of the transverse or space-like coordinates, the axis. So that means what you have here is exactly the same structure as I have here, except that you have a horizon that sort of sits here at some value u is equal to us. Okay. So this is what the black break is.
But I think more importantly, there's also singularity at u equals infinity. And that's like the horizon, which is just a coordinate singularity, u equals infinity. Now there is a curvature singularity. Curvature.
Right. Yeah. So you're exporting
this is really different. The first metric has no singularity. The second one has singularity.
I guess what confuses me, but this is just because I haven't done any of this stuff ever. I thought that empty space is when the Einstein equations have 0 on the right-hand side, and something in space is when you have non-zero. But this is with 0 on the right-hand side,
right.
Still call it non-empty.
Right. So if you have a Schwarzschild black hole, it has no energy momentum. Think about that. The idea is basically that all of the energy has collapsed and it's inside the black hole. And Yuri was pointing out that the nature of this singularity is such that it is just a coordinate singularity. So if we choose different coordinates, we can actually penetrate this singularity. There's no actual curvature problem there. Again, in complete analogy to a Schwarzschild black hole in AdS, in M4, Minkowski 4. He also sort of pointed out that there is an actual coordinate singularity at u is infinity in both of these spacetimes. But as long as you have a black hole, the fact that you have a horizon there means that nothing can ever actually escape here. So it's completely unimportant that we have a curvature singularity. So we will not have to deal with that ever.
So, I'm sorry, just in terms of notation, I would call this an AdS Schwarzschild black hole.
No, it's not. An AdS Schwarzschild black hole would be something where you have a factor in here that actually is spherical. That's what Schwarzschild. So, I mean, this is very legitimate solution. This is not very good. So
okay, fine, but right. All right. But what you call black brain is
yeah, this is the black brain solution. Other questions? Okay, very good. So we have this black brain solution. Now, how do we sort of make contact with our fluid? Okay. So the idea is as follows. We can take our metric here, and what we can do is we can, what is the, yeah, why don't I do that first? We can sort of describe, well, approximate this metric now close to the location of this horizon, close to the event horizon of this planet. Okay. So for clear horizon limit, the really sort of is not very very sort of complicated. All we have to do is to say that U is US times 1 minus a small perturbation. I call this rho. You plug this into, this is a coordinate transformation, you plug it into this line element here and throw away all the terms that are basically higher order in rho. And what you find is a line element that sort of looks like this. So L squared 4 rho squared over US squared. And I write this in a funny way. I write this as D IT squared plus dx squared over US squared plus 0 squared. It's just, okay, I put the minus sign as an I in here. And the reason that I do that is that I now say, oh, but let me think about a system at finite temperature. If a system at finite temperature, then the way I sort of set up problems in B-theory is that I code to so-called imaginary time. The idea being that if I go from T to minus I tau, where tau is now imaginary, the way temperature comes in is that I sort of compactify the interval in imaginary time such that tau runs from 0 to 1 over the temperature. Temperature is the inverse length of the thermal circle. So let's do this here. So periodic, yes. Let's put this in here, then we can basically just replace the IT here by tau squared, and we get something that looks like this. Okay. Fine, right? So Euclidean metric, the horizon, fine. The next step is to sort of see that, okay, I can write this as, let me write the whole thing. L squared, I want to write this as V rho squared plus rho squared V2 tau over US squared plus dx squared over US. Okay. And now I will sort of give this particular combination a second name. I will call 2 tau over US, I will call theta. Okay. Then we have a metric for Euclidean spacetime that sort of starts out as rho squared plus, sorry, d rho squared plus rho squared d theta squared. So it's a two-dimensional sort of patch of the metric of the spacetime. And if you sort of think back about your Jackson issues, what is the requirement on this variable that we have to sort of impose such that the spacetime doesn't have any issues? Students who took Jackson, please. What do we have to impose on theta? Say it.
The defense of the students saying silent Jackson doesn't talk about this way. It writes polar coordinates, but doesn't talk about singularity.
I'm pretty sure there's a discussion of what's known as the conical singularity. There we go. So the issue simply is, so the theory says that I shouldn't be asking too much. So let me sort of point out what does somebody sort of want to answer? So basically what you have here is a spacetime that has, if you want, some sort of polar radius and some angle. And the idea simply is that if the angle is periodic in 2 pi, then let me sort of make a drawing. So if I have rho in one of these directions, rho is along this line, and theta basically sort of goes the other way. And if this thing is not periodic on 2 pi, then basically sort of the space-time or the structure of the space-time will sort of have this shape here, okay? Because it doesn't go over to 2 pi, it will sort of end earlier or later. So what that means is that you have to identify this thing with that thing, so it basically you glue it together, it's like a cone. Okay, so maybe I can do this with that. That's fine. That's useful for something. So you would get up something that should look like this. Okay, this is something that has a point, so there's a conical singularity at this point.
that would mean we would have a singularity in our spacetime that's outside of the horizon. Okay? That's bad. Okay? It's a naked singularity in a spacetime. We really, really don't want to have that. Okay? So we want to forbid this. And the only way we can forbid it is to say that the periodicity of whatever this is has to be exactly 2 pi. Because then this thing sort of closes off, and we have a spacetime that looks like this. There's no conical singularity. The upshot is that, so theta must be periodic, this thing must be periodic with 2 pi. So basically we need to have that 2 tau over US, the periodicity of this must match 2 pi. I said that tau has to be periodic in 1 over t. So basically this has to be equal. And this means that if I bring US on the other side, US has to be 1 over pi t. Okay. Physically, what this means is that the location of the horizon, this is this US, is proportional to, with a factor of 1 over pi, which you just calculated rigorously, to the temperature of the field theory. Or physically, this temperature, of course, corresponds to the Hawking temperature of that black hole. Okay. So that's the first entry in our dictionary between the fluid and gravity, that the Hawking temperature of the black hole, black brain, corresponds to the temperature of the fluid in our field. And here it's a global equilibrium situation, so the temperature is sort of globally the same in our fluid, and it's globally the same in our black. Yes?
If you didn't force it to be exactly periodic at 2 pi, would you have a real singularity, or would it just be a bad choice of coordinate?
No, it would be an actual sort of singularity.
Like the curvature?
Yes, there would be a curvature singularity. If you have a cone with the tip, it actually has a curvature singularity. Other questions? Okay, I mean, yes. So what do you do with this? Okay, so we have one entry, maybe we can sort of get other entries for this whole dictionary. And the answer is yes, we can. So we have our black brain that's sitting in there. So next what we're going to use is the relation that says that there is a relation between the area of this horizon, and beware I say area, but in one more dimensions it's actually a volume, but we still call it the area of the black brain. And the entropy associated with the microstates in this black hole. And the sort of relation simply is that the area of the horizon divided by 4 times Newton's constant in 5 dimensions has to be equal to the entropy of the black hole. So this is just a Wittgenstein-Hawking formula for the entropy of the black hole, just in 1 dimension.
M4 is clearly has an infinite area.
Yes.
So doesn't that plane also have an infinite area?
That's correct. You'll see what it will drop out on both sides of. So we'll talk about the entropy density rather than the entropy.
You have the whole universe filled by positive.
Right. So let me sort of show you how this sort of story goes. And the thing that I sort of need is, first of all, I need to calculate the horizon area. That is fairly simple if you sort of took a GR class. So you basically sort of calculate the integral, which now again, because we are in 1 dimension higher, is not a volume integral d3x over the transverse coordinates of the induced metric on that horizon. So it's the determinant of G mu induced. G mu induced is the metric on that sort of lower dimensional surface. I can give you the details of how to calculate this, but again, it's not very sort of useful. Essentially, you can always stare at this, and I will tell you that okay, the induced metric is basically the metric given by this line element where you forget this term and you forget that term, because both of those are the transverse coordinates. So it's just this thing here, and then you take the determinant of this, you get 1 over US to the 6, you get the square root, you get 1 over US third, So then what you find from this is that the area of the horizon is nothing else but the volume that you get from this integral here over US3, and I didn't talk about the L here, there's of course also an L3. So that's the area of the horizon of the 5-dimensional black brane. And we almost have everything together to sort of calculate the entropy density. The only thing that I still need to tell you about is what is the value of G5. And for G5, okay, there's no sort of easy way to really get this. To get G5, really I have to talk about string theory and how you do a deconstruction of the original 11-dimensional theory down to 5 dimensions. I will spare you that, and I will simply give you the answer. G5 simply is given by pi L cubed over 2n squared, where n is the number of gauge fields that you have in n equals 4 super EMS. Okay. So you plug these two things, so you plug all of these things in, and we find that this is equal to, what is it, V3 L cubed over US cubed, US given by pi T cubed, divided by G5, so we have pi L cubed, and then we have 2n squared right here. We can divide by the volume, the 3-dimensional volume, to get to density, entropy density. So S, little s, is S over V3, is then given by the following thing. The L cubed cancels, one of the pi's cancels, so you get pi squared. You have 3 powers of the temperature here. We have n squared from here in the denominator, and then we get 2 from the, I forgot the 4 here. We have a 2, but there's a 2 over there, so this is basically what we find, that this is the entropy density of the fluid on the boundary. Okay. Now maybe it's sort of easier to sort of think about the corresponding pressure, which, if you recall that the entropy density is simply given by the derivative of the pressure with respect to temperature, you can just integrate with respect to temperature to get the pressure, and then the pressure here is pi squared T4 n squared over T. Okay. That's the pressure of the theory that you're describing. What is interesting, and this is sort of more of a side comment, we can write down the pressure of 3 n equals 4 super AMLs by simply counting degrees of freedom. The idea being the following: one bosonic degree of freedom in relativistic field theory gives pi squared T4 over 90. Now we have gauge fields, so we have a factor of n squared. And then the specialty of n equals super EMLs is that it has the same numbers of bosons and fermions, and has 8 bosonic degrees of freedom, and has 8 fermionic degrees of freedom. So you get a factor of 8 for those. And then because the bosons count as 1, but the fermions, because of their statistical nature, count as 7, 8. This is the number of degrees of freedom that you get for the free theory. So if you stare at this, you can bring in the 8. You have 8 plus 7 is 15. So then this means you get pi squared T4 n squared. You have a 15 here. 90 divided by 15 is 6. Right? 6. So you find that the free theory has a formula for the pressure that looks similar, except that it has a 1 over 6. And what we have is a 1 over 8. So the ratio of this P over P3 is 1 over 8 divided by 1 over 6, or 6 over 8. That's the same as 3 over 4. Okay. So what we sort of have is that we're describing a theory that's conformal, that has a conformal equation of state, but it has only 3/4 of the number of degrees of freedom effective for your thermodynamic quantities than what we would have thought about the weakly interacting free theory. So the 3/4 is sort of a fairly well-known factor in the application of string theory to strongly coupled systems. questions up to this point? Yeah.
Factor 8 times whatever, we have 8 in front.
So n equals 4 superMs just has 8 sort of gauge field degrees of freedom.
Say that again.
It has 8 gauge field degrees of freedom, or 8 bosonic degrees of freedom. I should rather say it like this. You can easily understand it by knowing that n equals 4 superMs. Its parent theory is n equals 1 superMs in 10 dimensions. 10-dimensional gauge field has 10 degrees of freedom, but because of the sort of gauge fixing, there are 2 degrees of freedom left, like in a usual field theory. So you get 10 minus 2 is 8. So that's the number of bosonic degrees of freedom.
Like a general formula, thing like
For n equals 4 superMs.
yeah.
Right, I mean, it's F mu, or FAB in 10 dimensions. That's its Lagrangian, plus the fermions. We can take this offline. It's not a very complicated sort of way to get there, but that's the theory. So there's nothing that I can do about that. Other questions? Okay. Good. So we know we have a fluid. The fluid has a temperature T. It has some thermodynamic properties. The thermodynamic properties have the same equations of state as a conformal theory, but they have, for some reason, only 3/4 of the number of degrees of freedom. So we are almost ready to sort of go beyond this, and we will go beyond this by saying that, okay, we could have started with a fluid description and equilibrium, and it would have sort of had similar properties, but to really sort of go through the whole matching between fluid dynamics and the gravity description, what we then have to do is we have to think about non-equilibrium corrections. Okay, so we will talk about dynamics. And the way we sort of talk about dynamics is that instead of having a horizon that's just sitting there and doing nothing, we'll allow it to fluctuate. Okay, so we have a moving horizon that's sort of moving up and down. In this moving horizon, we'll have local fluctuations. And the local fluctuations will give us temperatures that fluctuate and velocities that fluctuate. So we'll build up fluid dynamics this way. So that's the physical picture that what we are doing. Before doing so, however, there's one more thing that I wanted to tell you. And yeah, if there are no more questions, I'll raise this and I'll tell you one more piece of information.
Can I ask maybe?
Yes.
One detailed question. You mentioned something very briefly, answering Ulrich's question with respect to medium for the Schwarzschild black hole.
That's correct.
And is it really correct? I mean, of course, when you actually solve the equation, you go for R not equal 0, and then there's nothing there.
Right.
But and then, if I remember correctly, you fix the efficient by matching on Newtonian gravity.
That's right.
So if you really honestly plug in the metric for Schwarzschild black hole Einstein equations on the left-hand side, don't you get the delta function with a mass?
Oh, yeah.
No.
I wrote a paper at Steam about that, and you let me out and we have this complete crap. So.
No, you don't.
You wrote about what?
That there should be a delta function in this right side.
No, you just take the line element and you plug it into Einstein equations, you get 0 on the right.
That's very motivating. So what is okay, but what is the physical reason?
Well, the physical reason basically is that okay, I mean, it makes no sense to really sort of talk about the inside solution. Okay. Really, so if you have a matching at the horizon of your space-time, the Schwarzschild horizon, and in that regime there is no energy momentum.
But if you take hypoxia,
Right. We'll talk about hypoxia. Wait, we will get there. So, good. So the other piece of information that I want to talk about is holographic randomization. Holographic normalization. And the idea basically is as follows. So if I wrote down my Black-Query solution, then as for the Rio squared, then so it looks like 1 minus u for US for dt squared dx squared plus du squared over 1 minus u for 4. Okay. Then I can do, okay, in gravity, the precise form of the line element is unimportant because you have diffeomorphism changes, same equivalent thing of gauge transformations in field theories. And as such, you can sort of do gauge transformations, diffeomorphism transformations, and the physics doesn't change, but the appearance of the line element will change. Okay? So I can take different coordinates, it will describe exactly the same physics. Okay? So I will sort of do a particular coordinate transformation. Well, why don't I write it down? So I call this Z, and it has this particular form, but it's not really important what it is. The point is that you can actually write it down. As 4 over root 4 minus 1. So there's this double square root, whatever. And if you plug it into this line element, you find a line element that is of the following form. It becomes L squared over Z squared times minus 1 minus Z squared over 4 US squared squared 1 plus Z squared over US squared dt squared plus dx squared times 1 plus Z4 over 4 US squared plus dc squared. So what is the sort of the idea here? The idea here is that first of all, I've introduced a new variable z that takes the role of my fifth coordinate u. Okay? However, it's constructed such a way that the boundary of my space-time is still at z0. So z0 corresponds to us, and then the rest is sort of somewhere at positive z. This coordinate transformation has the property that there are no mixed terms, dz dx or dz dt. And it has the property that the coefficient of the dz squared term is fixed to be L squared over z squared. This is just a particular, let me call it gauge choice. This gauge choice, this particular form of the metric where you don't have any, so no dz dt, dz dx terms, and that the d squared term coefficient is L squared over z squared. This particular gauge is called Stefan-Brayhan. And it turns out that you can always bring a 5-dimensional line element into this form. Okay. It's a mathematical proof.
So US is what value of Z?
That is a good question. So U is US is, what is it? So we get this falls away, so you get is square root of 2 US. Square root of 2 US. Second?
Is there a root 2?
I didn't hear.
I don't remember the root 2. Are you sure about it?
I'm pretty sure about the root 2. Yes. Yeah, but yeah, please prove me wrong. So this particular form of the metric is nice because in this particular form of the metric, you can actually sort of read off the physics by doing a boundary series in powers of the distance z from the boundary. Okay? So what I mean by this is that I take my line element and I write it as some term that's just L squared over z squared minus dt squared plus dx squared plus dz squared. And then I have corrections that go as L squared over z squared times, in particular in our case, you can actually sort of see that, can you see that? Z squared, yeah, so the correction to this is, let me sort of this.
Can I ask about the coefficient of the dx squared in the is that z to the 4th or US to the 4th?
Yes. Yes, it's C4 over 4 US squared, and I think what I did was that this is wrong. This should actually be C4s. And if you look at this and you're in your mind sort of do an expansion in powers of z, you find that since there are only Z4 terms here, then basically the next correction after the 1 is coming in with a Z4. So we have S squared over Z squared times Z4 times, since this one only has the 1, it doesn't contribute on the coordinate transformation, and we got that C and US have the same unit. So C with 4 over US squared is not. Yeah, you're right. Yeah, actually 4. Yeah, absolutely correct. Yes, yes, yes. Thank you. That was too quick. So what you find is that this comes in with a Z4, and since this doesn't contribute because it doesn't have a Z4 coefficient, it comes in with something that, let me just write it like that, dx nu times, if you want to the expansion of the metric to this order, the point being that the object that we get here is nothing else but the energy momentum tensor of the field theory that we described. So to reiterate, the message is that if you bring whatever line element you have in this particular gauge, and then you do a power series expansion in Z, then the fourth order term, the Z to the 4 term, that's the energy momentum tensor of the system you're describing. If you want to, the leading order coefficient is the metric G mu nu, dx nu plus Z squared that you're describing. The higher order powers would then correspond to correlation functions of your energy momentum. So this provides a direct sort of connection between, well, the line element on the one hand side, the energy momentum tensor on the other side, and if for some reason I now make my space-time dynamic, okay, so if my line element actually has time dynamics inside, I will get, or I can read off the time dynamics of my energy momentum tensor, of my 2-point function, of my 4-point function, whatever. So this is how you either feed in information into the space-time description from the boundary, or differently, if you have the space-time, the full bulk description, you can read off the boundary information by doing this. Okay. Questions on that?
There is an online question.
Yeah.
Which asks, what is TAB corresponding to the line element of length?
What is TA? Oh, no, wait a minute. TAB or TAB? Capital T?
Yeah.
Capital TAB. The sort of thing that I had before was the energy momentum tensor of the 5-dimensional sort of space-time. That was called TAB. If that's what it is, that would be the energy momentum tensor of your system that you have your Einstein equations on. In this case, I set it to 0. So I consider just pure gravity, no matter. There's only a boundary term which corresponds to the boundary stress tensor, but there's no bulk stress tensor.
So at 0, at leading order in Z squared, you get
The metric.
Contribution to S squared, which includes part in DZ, but at the next order, you get something that has only 4 space-time.
Yeah. Because your metric was brought in the gauge where this thing only contributes at this leading order and doesn't have any subleading corrections. That's precisely the point of it. And of course, if you sort of read off what this means for your energy momentum tensor here, then you find that the energy momentum tensor, and I was being a little bit sloppy because it's the energy momentum tensor times a constant, and the constant again involves this G5. So what you find is that this energy momentum tensor here is just T4 pi squared n squared over 8 times 3 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. If I plug in again that US is 1 over pi t. Expand this, claim this is what you get out. And this is, of course, the form of an energy momentum tensor of an ideal fluid. Okay. Epsilon 0 0 0 0 p 0 0 0 0 0 p 0 0 0 0 p, with p being just the pressure for the field theory that I'm just describing, that I have before. You get the full energy momentum. did I ask, was there questions on this, or are you already past this?
Sure, by the way, there is a square root. So I just
Okay, good. Very good. Okay, good. Good. So since we are on this, you can use this construction. Okay, you can use this construction because if for some reason you want to study a particular initial condition that involves an initial condition for the energy momentum tensor, you can use holographic randomization by constructing a dye element, basically from this. You can then feed into Einstein equations, and you can sort of see what the evolution of that system will give you. And they'll use that in order to sort of talk about energy deposition of collisions of strongly coupled sort of, what we call them, nuclei at the end of today's lecture. Before I do so, however, I want to sort of still finish up on, at least briefly, more or less briefly, talking a little bit more on Yuri's question on how you get the quasi-null modes to the black brane, and also talking about sort of non-equilibrium corrections of fluid dynamics. So this is fluid dynamics in equilibrium. It's an equilibrium energy momentum tensor, not particularly interesting. We want to sort of perturb this so that we have fluctuations and get out things like viscosity and stuff. Oh, and maybe I should say this, okay? So now we're doing a microscopic theory, so we get definite answers for all of these quantities, okay? All the transport coefficients have now definitive values. This is, of course, that the structure has to match the effective field theory that we've built up, but now we can calculate all the numbers that we sort of are interested in.
So these are the medium properties of
N equals 4 super and L set strong. If this is too much drinking from a fire hose, you have to tell me, right? I'm happy to sort of either slow down or sort of cover something more detail. I don't really need to go through all of this if you're sort of already lost. Okay, good. So we have talked about equilibriums. Now let's do near equilibrium. And basically what that means is that instead of having our line element be the line element of the black brane that I just wrote down for you, we're gonna allow perturbations around that. Plus, I write the perturbations as GAB, delta GAB, DXA, DXB. And we're going to sort of, for now, treat these perturbations to be small so we can do linear response. Okay? So because of this connection between what the bulk is doing and what our boundary stress tensor does, if we do perturbations in the bulk in our metric, this would correspond to perturbations on our boundary. So we're doing perturbations of the temperature, the fluid velocity, the horizon is moving, all of these things are happening, but we, at this point, only allow small fluctuations. Okay? And essentially, it's the same story, right? I mean, you sort of make an answer for your line element, you stick it into your Einstein equations, and you go solve. Okay? However, as you can maybe sort of guess, I don't know, if you plug this answer without any restriction into Einstein equations, you get a massive sort of coupled PDEs, which are sort of, let's say, even in the linearized form, are not easy to sort of solve straightforwardly. So typically what we do in order to sort of make the problem tractable is that we concentrate on certain channels. Channels, what do I mean by this? When I talked about fluid dynamics, I said there were different kinds of modes. Sound modes, shear modes. Well, guess what? You have exactly the same thing here. Okay, so there's a shear mode, a sound mode. There's also what's known as a scalar mode, which is not present in fluid dynamics, simply because we're doing 5-dimensional Einstein rather than 4-dimensional fluids, but well, so on. You can sort of decompose these perturbations into these channels, and you get three channels: sound, shear, and scalar. Sound is the most complicated one. Shear is sort of medium complicated. Scalar is by far the easiest. I have 20 minutes left. I will do the scalar. Scalar channel, which means that I only turn on G12 is G21 as a function of just G and Z, and all others are mentioned. The way that I will sort of solve this is that I say that I sort of do a Fourier transformation of these things. So this is e to the minus I omega t plus I k. This also depends on u, of course. Z, and then I will have a phi here, and I do another coordinate transformation, which is not really important. But sort of write this as u. This is phi of v, where u is us squared of v. The point being that I want to have my horizon be sitting at v is 1 rather than u is us. Okay. It's not important, but if I change notation now, then there's no way that I can get anything correct. Okay, fine. So into Einstein equations, and you get out a single differential equation that you have to solve. V double prime, phi double prime minus phi prime, 1 plus v squared over 1 minus v squared times v plus phi of v us squared omega squared minus k squared times 1 minus v squared divided by 4v 1 minus v squared is 0. So this is the determining equation for this metric perturbation. The way you solve this is as follows. You stare at this equation, and you sort of stare at it first close to the boundary. So close to, you find that this is a differential equation of the Hooksian class. It has characteristic exponents 0 and 2, which you all would have guessed immediately, I'm sure. Anyway, so this means that a phi of v sort of goes like v to the alpha with alpha is 0 of 2, so you have 2 branches of solutions, basically. The way you sort of implement this is to say that phi of v then sort of can be written as a superposition of these two with coefficient functions a and b. So CA, this depends on b, and this depends on b. This is the solution that starts at v to the 0, so it's constant. This is the solution that starts as v squared, so this is the second one, and they come with 2 coefficient functions a and b. And you can calculate these coefficient functions, again, by sort of doing Einstein equations. I can give you as much detail as you want in this, but the point is that once you have these coefficient functions, this then determines the 2-point correlation function in Fourier space, and it's given as the ratio up to some prefactor n squared t4 over 2 of this function b over the function a. Okay. So once you sort of do this exercise, you extract these functions a and b, you get the correlation function of the energy momentum tensor, beta 6. This is the correlation function t12, t12 in Fourier space. So you get a 2-point correlator. Okay? That's what you get from this exercise. And because you get a 2-point correlator, remember that I said at some point in my lectures that the analytic structure of what we're doing is encoded in the analytic structure of the 2-point correlation function, because then you close the contour, you sort of pick up all the singularities in the lower half plane. Well, it's just the singularities of this thing that will determine what the analytic structure of the problem is. So this will have all the modes that we need. So it's just looking at the singularities of this. It turns out that for n equals 4 super MLs, the singular structure is such that A has poles, and these are the poles that determine the singular structure. Yes?
Is that T12 in the boundary theory?
Yes, that's T12 in the boundary theory. That's correct. All of these are in the boundary theory. I didn't really sort of say this. Okay, so how does it? What's the question?
Somebody's.
Oh.
Can I ask a question?
Yes.
Sorry, why is it so? Look at the scalar, right? If I remember,
Yeah.
right, scalar couples to, so it's like a dilaton, right? So
Yes.
it's the dilatation modes.
Right.
So it's more like, you know, f mu squared, correct? I mean, if you want to look at T12, T12, you need to look at the graviton.
No, but this is the graviton. It has a scalar channel, and that's the scalar channel. There is no dilaton in this here because I haven't turned on the dilaton. It's just pure Einstein gravity. I mean, it looks the same, right? It looks the same, but in pure gravity you have this channel, and you can calculate.
Okay, and the green function to calculate it, you have to differentiate the action with respect to the boundary.
That's correct.
Which
In order to get this formula, the relation between these functions that I just calculated and the Green's function, there is a lot of extra technicality that I have not talked about. You indeed need to sort of have an action for the theory. And you need to be very careful about renormalization, really normalizing that. But that's the outcome. Okay? So once you calculate these functions, this is what you get. So let me just show you what it looks like. Where A has simple poles. It looks like this. It has a plot. Simple zeros, which means that G has simple poles. So the structure is like this, that you get this Christmas tree structure, where these guys here really have to get them numerically from determining the series of some polynomial or something like this. And they are loosely located at 2 pi t times plus minus 1 minus I times n, where n is 1, 2, 3, 4. So these are the non-hydrodynamic quasi-normal modes of the black brane. And because this Green's function determines the response of the energy momentum tensor in this channel, e to the I minus I omega t, if you close this integral, you pick up all these poles. These are the sort of solutions that you get in the real-time dynamics of a system. So that directly connects what you find in the fluid dynamics of this theory, n equals 4 to Mills, to what the macroscopic structure is. And you can calculate all the precise way that these modes are sort of damped, all of their damping rates you can calculate exactly. You can also calculate the oscillations that you get. Everything sort of is built. Questions?
So what is the pole structure in other channels?
Right. So very good. Thank you. I wanted to say that, but I forgot about it. The scalar channel is special. We haven't talked about the scalar channel in fluid dynamics. The reason is that there is no fluid dynamic pole in that channel. So in the cases that I sort of have talked about before, I said here are the sound poles, here are the shear poles. There are no such poles in here. This channel doesn't have any of these poles. This is the reason because it's so simple. So in the other channels, the sound and the shear channel, what you have to do is that you get an extra sort of self-consistent equation that you need to solve on top of this. And then you will get essentially also this Christmas tree structure with slightly different values plus the hydrodynamic modes. But in order to show that, it's slightly more complicated than what I've done in the scalar channel. However, there's one big bonus that we get in the scalar channel. And the big bonus is that we can, so you can go back to my lecture on Navier-Stokes, essentially. And you can calculate the two-point correlation function in Navier-Stokes. And I didn't sort of talk about this, but so in Navier-Stokes, you can calculate T12, T12 as a function of omega and k. And because we're doing a gradient expansion, we have to expand this in gradients. And you find that this thing goes as constant minus I eta omega plus higher order terms. Okay, where eta is the shear viscosity of the shear mode in fluid dynamics. Now, what you get here is we get the full function G12 in n equals to super mLs. We can take this function and now not look at the analytic structure, but just expand this in powers of omega. And what we find is the following. So G12 now in n equals 4 super mLs of omega and k has the structure constant plus S, the entropy density, minus I omega over 4 pi, plus other stuff. And since we know that the gradient expansion is the universal limit of all macroscopic theories, and we calculate this thing in one particular macroscopic theory, n equals 4 super mLs, we can match the two terms and read off the transport coefficients for n equals 4 super mLs. In particular, these two terms have to be the same. They both have the structure of minus I omega, so this means that eta in n equals 4 super mLs has to be equal to S over 4 pi, and this means that eta over S in n equals 4 super mLs is just given by this well-known ratio.
Now we lost me.
Oh.
So actually, scalar mode is something that exists only in this gravitational theory, but not in hydrodynamics. So how did you make the connection between those?
Right. So it's true that the scalar mode is a purely gravitational mode. It is not dynamic in field theory. However, in fluid dynamics, sorry. But what you can do is you can calculate correlators of the energy momentum tensor in fluid dynamics. So, okay, maybe this was too quick, but this correlator is nothing else but the correlator Txy of Tz, Txy of Tz, Fourier transformed in fluid dynamics. And that is a correlator that doesn't have hydrodynamic pole.
Txyx, two different.
It's not local. It's not the same.
Right, so let's start 0. Yes, thank you. So this is a correlator you can write down. This is the correlator that you get your Kubo formula for the shear viscosity. This is the Kubo formula for the shear viscosity. And I can just calculate this correlator in gravity. That's what I just did. And then you can compare and match. Yes.
So are you saying like you're trying to make a connection between this scalar mode and this consider space to the shear viscosity and the plot?
No. So the scalar mode is a particular property of gravity. All I use it for is to calculate a boundary stress energy coordinate. That's what I use it for. Right? I mean, how do you calculate shear viscosity in any theory? You calculate a stress energy correlate. It so happens that the corresponding calculation on the gravity side is easiest in the scalar channel.
So what this doesn't describe any fluid dynamics, but you can calculate the linear response coefficient also in that mode. That's what you use.
Under the hood, it does have fluid dynamics. It's just that it doesn't have fluid dynamic pole or mode. There's no scalar fluid mode. But what's going on is that the horizon is wobbling. There are small fluctuations, and that's the reason you can actually get this transport coefficient. Of course, the thing that you can do is you can sort of say, okay, fine, I don't believe it. Let me calculate now in the sound channel. And if you do the thing in the sound channel, you'll find sound nodes. You can calculate dispersion relations and extract the shear viscosity this way by comparing to the shear viscosity in the dispersion relations of usual fluid dynamics. And you get the same answer. But this is by far easier, but more straightforward way of doing it. And it gave us this non-hydrodynamic quasi-number modes that you really wanted to have.
So I missed what you just said. So there's not a single hydro mode. I thought in your Christmas tree top 2 one of the hydro.
No, these are in the scalar channel. There are no hydrodynamic modes. It's just in the sound and the shear channel.
I wanted to find what
You calculate the sound of the shear channel.
what
The sound of the shear channel. So you have to turn on metric perturbations that, for instance, couple to energy density, so it's 0. Or you calculate perturbations that have, for instance, the 1,3 component that couples to the shear.
Okay, and the loss was not reduced to the scalar, like T1.
It's a different channel. So
Right, well, so this is actually fits into my previous question. I looked it up, so if I remember it right now, phi, of course, not finite. So your T1 2 couples to the 1, 2 component of the metric.
yes,
And really that's what you want to source. But then, for various reasons, this 1, 2 component of the metric, the equation, is equivalent to the scalar equation.
yes,
And that you connect. So it's
Yes.
not an honest about scalar field, it's just the equation.
yes, that's right.
And then what you're saying now is if I do the same for say the 0, 0 component of the metric and the 1, 3 maybe, the same miracle doesn't happen and I don't get the same scalar equation, I'll get something else where I would see the height.
That's correct. Yes. Yeah.
Okay.
Yes.
Very good.
So fine. So I didn't really get to what I still wanted to talk about, which is sort of to go a little bit deeper than just these near equilibrium studies. But that's, I think, perfectly fine. I think we covered a lot of sort of ground in the lecture for those of you who have not sort of had a lot of exposure to GR, I guess. So I will see whether there's some more questions or things that we discuss, because really for my next topic, I would need more than 5 minutes or so that I have.
This probably went very high at the upper limit of our, so it's difficult to ask
Right, right.
meaningful questions.
Right, so-
Checking you.
Right, exactly. So I think what you should take away from these things is that there is a well-defined way to calculate, to match fluid dynamics to macroscopic theory in the strong cubic limit, and it was for super EMLs. You can get all the transport coefficients that you want. And something that I didn't get to, you can also use this in non-equilibrium situations. So what I'm talking about, of course, is you can sort of, the way to sort of do it, let me sort of say in words what I sort of had prepared, is think of a boosted charge in electromagnetism. Okay? Then your energy stress tensor will be, you can calculate it in some regime, it will have delta functions. If you can calculate the boosted charge energy momentum tensor, you can plug it into a line element so that you get a sort of strongly coupled version of this. So think now you have your charge on the boundary, but it sort of has a stress energy tensor. Make a picture. So this is my space-time. I calculate a boosted charge. This has an F mu nu. From the F mu nu, I calculate a T mu nu. I use holographic renormalization to basically sort of calculate a line element that corresponds to this T mu nu now on the boundary. Add picture like more like this, something like that. We have a moving thing. And then I can sort of double this and sort of have two of these guys that come in. And I can solve Einstein equations for this problem, at least for short times after the collision. And then I get a fully highly dynamical sort of result for what's happening to the energy before fluid dynamics actually sort of becomes applicable, because I'm now very far away from equilibrium. And I can calculate initial conditions from fluid dynamics from this problem. I will sort of let this stand there. And maybe in the second version of the lecture course, we can discuss this. Yes.
So when you fluctuate the line, right? You often imagine the tensor that's in the ideal field. Do I see Navier-Stokes corrections appearing when you fluctuate?
Yes.
Or more or something else?
Right. Yeah. So the question is, what happens if I sort of did a little bit more than what I did here, namely I actually look at the fluctuations of, let's say, the fluid speeds on the boundary and the metric and the temperature. And yes, you get a one-to-one matching to Navier-Stokes with the transport coefficients given by the theory. in fact, there are people who have been writing papers to say that you can try to use gravity and area theorems of horizons to try to prove existence or non-existence of Navier-Stokes solutions, because there's a one-to-one match between these two things. My understanding is that has not completely worked out, because even though you have area theorems, they are not particularly well suited to proving the existence of Navier-Stokes. But yeah, so there's a one-to-one correspondence. It works out beautifully. My understanding is you can actually push it to much higher orders than if you were to try this in an actual field theory.
If that had worked out, we would know about it because it's a millennium. Right?
Yes, yes, yes. Somebody would help. Okay, so thank you very much for your attention.
Paul, let me thank you personally again for.
Sure, of course. Sure.
It was really nice for you to fly all the way over from Boulder to teach this class. And as you know, there were not just the students here in the room, but also others. And then there were the ones who figured out that they can watch the lecture later and take some course in the meantime that would otherwise have conflicted. So that's explains some of the people who are not here today. Sure. All right, so thank you very much.
Sure.
It was very, very, very good for us, and I learned a lot. Maybe not from the last lecture, that was way too high for me, but from the previous two, I learned new things. That was it's very valuable for me, and I'm sure it's the same for others. All right,
Thank you.
thank you.
Sure.
This way, so it should be